Hi, it's Robin. I've had a lot of requests to talk about how I developed my C-64 games back in the day, especially Minima, Splatform, Frogs and Flies, games I've mentioned on my channel before. So I'll talk about another game I made that nobody has asked about. It should be just as informative, so don't feel ripped off, and it'll give me a chance to figure out how to best make a video about game development, as I want to make some videos about those other more popular games. So once I got this idea, I searched around my basement for a couple days and finally found this box, 3.5-inch discs from the late 90s and early 2000s, and this is where I saved all my source code because I was using 3.5-inch discs with my FD2000 back then. So actually all my source code was in here, and I couldn't find my backups. I could have sworn I made backups to like my PC or something. No idea where those went. So once I finally found this, I did back them all up again to SD card. So this is the particular game. So I didn't even bother using labels a lot of the time back then. I wrote a marker, and then in, I guess that's pencil, Marz. That's the name of the game. From 2001 to 2003, I participated in something called the Minigame Competition. It wasn't like Nintendo-style mini-games from the Wii era, but rather games coded with a very tight size limit. In 2001, there were categories of 2 kilobytes, 2048 bytes, and 512 bytes, and I won the 2K category with my mini RPG Minima. Then 2002, there was a 1K category, and I won with a little platformer called Splatform. In 2003, there was a 4K category, and I won with an expanded 4K version of my RPG called Minima Reloaded. I also entered the 1K category, but I did not win with that one. And so that's this game, Marz. So I'll load this. If you look in the description, there will be a link to download a D64 with some of the files so that you should be able to build this yourself. So I'm loading Turbo Macro Pro. I again have my Super Snapshot and REU, and this is exactly the system I used in the late 90s and early 2000s to develop games. And we start Turbo Macro Pro with 32768. This is the older version 1.05. That's what I was using then. And we'll load the game. Not sure why I called it MM29. Mini Marz, I don't know. And version 29 of the code. It's actually a version 30 of the code, which is extra optimized. And I don't think I'll get into that today because this is going to take long enough just to go through the code. But I'll include that. It has to do with a tiny decompressor called Zip, XIP, by Stephen Judd. And it's a few tweaks to allow this game to compress with his mini compressor. And that could be its whole own video there. But you might want to read the documentation for that. I'll include a link to his old website where you can download that and check that out if you want to. Okay, so here's the source code, and we're going to go through it in detail today. I haven't done any cleanup on this code, and as I said, this was written in a hurry in 2003, so it's 16-year-old source code, was not documented very well. We're going to look at it as it was. I want to mention that Terry Cavanagh, I believe that's how we say his last name, is a game developer. You might know him from his game VVVVVV, 6 Vs. That is very much a Commodore 64 style, and he released the source code to that game recently, and lots of people on Twitter complained about how terrible the source code was. And I was almost worried that he was going to regret having shared it, but he did roll with it well. I'm a real fan of Terry's work. That game and Super Hexagon are great games in their own right, and he totally surprised me when Apple did a feature on his iOS games and was asked to share 20 of his favorite indie games. And he mentioned one of my games for iPhone, which I made with my partner Sam at Pixel Games, the game Foreigner, which actually I showed a C-64 preview of a little while ago on this channel. Anyway, he nominated that as one of his favorite 20 or whatever indie games, so what an honor. So anyway, my point is, we can share our source code, particularly for games. Sometimes source code is rotten, and it doesn't mean we have to be proud of it being terrible, but at the same time, the important thing is getting that game done. Good source code, especially in game development, to me really is secondary to just getting that game done. It's hard enough without worrying about how pretty your code is. Now, in other areas where that's your main job, and especially when that code is going to be maintained and supported, like in business applications and so on, and bigger teams where there's lots of developers, of course, good code is important. But when you are coding games solo, that's a risk you might want to take. I'm not telling you to purposely write terrible code, but don't get too hung up on that when it's the difference between getting the thing done or just not being able to deliver the game at all and just giving up on it. Of course, bad code might make you give up on it. Anyway, it's a balance. I'm not going to talk about that forever. Just not going to apologize for the code being bad, but I'm going to warn you. Okay, we'll try playing the game here. Fortunately, I left a few notes to myself. Some graphics have to be loaded into memory. They're not included in the source code. They're binary files. This is something I failed to do in some of my projects. Always worthwhile spending a few minutes, even if you don't document the code, at least all the, let's call them dependencies, such as where graphics belongs or whatever, always make a note to yourself on that. It might be the difference between you finishing your project or just giving up on it after you take a break for a couple weeks and then you can't remember how to get going again. So back arrow, Shift+R brings up the REU menu, and we're going to load. This is to load a binary into the RAM expander, which will then be mixed, so to speak, into the bank, and then it'll be part of the code that's transferred from the REU into 64 memory when you build. So it's a way of including binaries. And that file name is I said UFOSPRITE at the top, but it's actually UFOSPRITES. And the memory location that has to be loaded to is 3F80. And actually it loads into, I think there's 4 frames of sprites here, but I'm only using one of them. I'll explain that more later. Again, back arrow, Shift+R, brings up the REU menu, load, laser beam 2, and we're going to load that to 3FC0, which is actually just 64 bytes after that UFO sprite. So we're loading this into the middle of the UFO sprites. Okay, we'll get into that more after. Okay, so now we've loaded our sprite graphics. Back arrow 3 to build. We'll just check out the game. Now this game's kind of ugly and kind of awesome. I'll show you what I mean. So that UFO ship is super detailed. Okay, anyway, the goal is to drop bombs onto, I don't know if that's a city below or a cannon. Anyway, like I said before, I find it hard to talk and play video games at the same time. Anyway, the goal is to eliminate all those blocks below. And those are what's really ugly about this game. That sprite is super nice. It was made by a guy named, goes by the handle of Diversion. Oh, I'm doing terribly here. There. And you get bonus points once you clear them all. So that's level 1's pretty easy. And then you have to move the joystick to start the second level. So yeah, Diversion made that sprite, and I ran out of memory basically to make nicer looking graphics for the actual level. So you can only shoot one bullet or bomb at a time. This was actually modeled off of a Flash game that I was playing in, well, I guess at the time, in the early 2000s, that I thought was kind of fun and original. Well, turns out this is a really old genre. There were a whole bunch of VIC-20 games. I think it's called the Bomber genre. And I was just totally unaware of that, even in 2003. Uh-oh. Okay, and I got to shoot out every second one is the strategy here. That should be okay. Woo! You get the idea. The ship keeps going faster each time, and the bomb, whatever they are, the buildings or the, I should decide what to call those. Okay, you get the idea. I've rigged it up so you hit restore to re-enter Turbo Macro Pro. Oh yeah, it's game over when you hit one of those buildings. Me and Sam at Pixel Games actually released a collection of little games called Pixel Party for iPhone. I don't remember if we did it for Android or not. And one of the games in that was Marz. And we did a C-64-like version of this game. And actually, it looks really great. Sam did the graphics. I'll show a little video clip of that here, just so you can see what this game could look like if I put the time into it and didn't have the 1K size limit. Okay, so F1, or actually F2, to pop up to the top, and we'll just go through this. The code starts at 4000, and you'll notice I put the sprites right up against that at 3F80 and 3FC0. So last two sprite slots in bank 0 of the VIC memory. The VIC can only access 16K, so this is the very end of that first 16K bank, and then the code's butted up right against it. Just an attempt to try and make everything as tight as possible. Then we're going to define a whole bunch of zero-page variables. When you try to make a tight game, well, at any time, if you need it fast or to use less code, 0-page is the place you want, because it saves a byte and a cycle, in most cases, over using a 16-bit address. Some of these variables are self-explanatory. I was kind of careful to use only certain ranges of 0-page because while I'm not using any of BASIC, I am using a few kernel routines, and they still require some 0-page to be left alone. So I found that these were safe addresses. Screen memory is at typical 1024 or 400 hex. And the level data we're storing up at C1000. I'll get to that later. V is where the VIC address starts. That's a tradition that is from the C-64 Programmer's Reference Guide. And this is a bunch of SID registers for the sound effects. Again, that's where the sprite definitions are. Those are just comment to remind ourselves. 254 times 64 bytes per sprite in hex gives you this address right here. And 255 times 64 converted to hex is this address. So those are the sprite pointers. There's 256 different potential sprite pointers. Of course, you can't actually use 256 sprites at once. Well, unless you're really clever, I guess, because you need character data and, in this case, screen memory. Well, all that has to pack into the 16K. But there's still 256 potential sprite pointers, and it's up to you to arrange them. All right, game init. So this is our first bit of code. All this was just definitions, no codes generated. First thing we're going to do is reinitialize the input-output vectors. That normally wouldn't be necessary, but that compressor that I was talking about, XIP zip, requires that, and you can read about that in the documentation for it if you're curious why. And then we turn off the kernel interrupt that handles the keyboard scan and so on. We don't need that, and it saves some CPU time, so it's typical practice to control the IRQs in game development. These lines, I've shown this before. In this earlier version of Turbo Macro Pro, the jump back routine's at 384. I think that got moved to 320 in later versions. So this is just pointing the NMI vector at the Turbo Macro Pro jump back routine And that's the trick that we're using so that we can just hit restore. And while we're testing our game, it'll pop back here to Turbo Macro Pro. That could be removed in the final version of the game. In fact, it should be. And then we set the background color to blue and the border color. And we initialize the SID, including the volume. I am not sure why I left those comments, but anyway, that's saying the volume. Okay, so this outer loop, game init, only happens one time when you run the game. The very first time it's run, game init happens. So that's just one time. But then each time you start a new game, as you get game over and start again, then this play init happens. So these are almost like nested loops. You can think of them that way. We'll go a bit deeper soon. So when a new game starts, we're just going to zero out these important, you can call them variables or memory locations. The level pointer, zero out your score, your level number. The level pointer is for the level data. We'll look at that later. The level number. And these are for frequency counter 1 and 2 are involved in making the sound effects. Okay, then we've got a block. That's just so we can reuse labels inside there, like this loop, rather than me calling them loop 1, loop 2, and so on. This is Turbo Macro Pro's solution. And we are going to fill color memory with 15, which is a gray. And this is color memory here. And we're doing a little trick here. Because we have only 8-bit index registers, that's a maximum of 255. Screen memory and color memory are 1000 bytes. So one way of filling all of memory is to split it up into 4 chunks of 250. So that's what we're doing here. But the reason we're subtracting 1 and adding 249, instead of, you might think we should just go D800, and then this would be plus 250, like splitting it into quarters. The reason to use this kind of funny math is so that we can start at 250 and decrement and just check for branch if not equal to loop. Once you hit 0, then we're done. But it never gets to actually store the value in memory at this location, comma 0. It's the lowest x gets while in this loop is 1. Whenever possible, in 6502, we try to decrement because we're able to check for this 0 condition easily. So it's a little bit ugly, but that's the reason for doing it. It avoids us having to do a decrement and then comparing x with either 255 FF if we're going down, because we want to do a loop with 0. Anyway, it saves a couple bytes. And then we're going to fill screen memory with 32, which is just a blank character in the default C-64 character set. And it's the same trick, filling screen memory, 4 chunks of 250 characters each. And then we're initializing the ship's speed to 3, which is actually 1.5 pixels per frame, because we're using, I guess we can call it fixed point math. Basically, this number is going to be divided by 2. I'll show that later. And that's the speed for the first level. Okay, now our game is initialized. And now, like I was talking about the nesting, we have a level initialization. Each new level, this code is going to execute. So it's kind of like the scope is changing. The one-time game run, the per game run, and now we've narrowed down to the point where we're initializing our level. So level number was initialized to 0, and now we're setting it to 1, which is a more human-readable first level, rather than saying the first level is 0. Now that we've incremented the level number, we're going to check if the level pointer, and this is the data that makes up how those buildings, I'll just call them buildings, this is a pointer into that level data. And because each level is 10 bytes, the definition for it, and we have 5 unique levels, we're checking for 50, and that will actually cause a wraparound. If we get through level 5, it's actually going to go back to the data for level 0, but the speed is going to continue to increase. So even though the game wraps around, the speed, you'll play those levels over again at a faster speed. And actually the level will still go from 5 to 6, but it'll use the level data from level 1. Okay, and we're just checking to make sure that it's not equal to 50. If it is, we set it back to 0, and we increment the speed of the spaceship. Maybe I said that the speed of the ship increases each level. It does not. It looks like it actually only increases once you've wrapped around, but the level becomes more difficult because the buildings are taller. Okay, now we've gone ahead here, print the level number, and we're using this kernel routine called plot to move the cursor to near the top right. Notice that the X and Y are reversed. That's common in 6502, that you have to use Y, the Y register for the X position on the screen, and the X for the Y position on the screen, because of how indirect indexed addressing works. It uses Y, and because of how screen memory is mapped across, you end up having to use Y. Okay, and clear that to set the cursor position. And then we're just going to print out, this is text 3. I think that just says level. Yeah, here's our little definitions. It's looking for a 0, a null terminated text string, and text 3, I could have just called that like level text. I don't know why I didn't. And there's also one here for score, text 1, and then here's a game over message. Okay, so that prints the level text, and this is a kernel routine to print text to the screen. We're saving some bytes here. Normally in games I'd probably make my own version of these routines, but because I was trying to squeeze this game into 1 kilobyte, I'm using the kernel routine. And here I'm using this BD-CD routine to print out the level number. This is an accessible routine where you load the low byte in X and the high byte in A. And of course, well, I guess if anybody could survive past 255, level 255, then it would wrap around to 0. I think it's probably impossible. Famous last words. Now we're going to set up the sprites. And you can check your programmer's reference guide for each of these. For example, register 1C is turning on multicolor mode. DO1C, I set V equal to 53248, which are D000 hex. So that's turning on multicolor mode. Registers 27 and 28, 27 and 28, that's the sprite 0 color and the sprite 1 color. So that's both for the main color of the spaceship and of the bomb. And then the multicolor mode is white, multicolor 2. So this is just saying the colors of that spaceship and of the bomb. And this is saying the sprite definitions to 254 and 255. So they're the sprite pointer definitions. Then we're enabling those 2 sprites for the spaceship and for the bomb. And this is setting the sprite position. Actually, this is setting the ship X, which is twice its sprite coordinate. So we'll look at the routine that fixes that, and we're directly setting the Y coordinate. So we are abstracting, in a sense, the X position of the ship into its own variables that will then be converted into sprite coordinates, but we're directly saying the Y coordinate of the sprite. And this is all just for memory savings. Ideally, you'd probably always keep your object variables separate from the VIC hardware registers, the sprite hardware registers, but in this case we're doing a one-to-one between them. Okay, and this is the high bit. If you see my joystick controlled sprite video, I talk a bit about this, but basically this is the 9th bit of all the sprites packed into one single byte, because the sprite X position can be greater than just 256 different pixel positions. This is the Y coordinate of the missile. We're zeroing that out. I'm not sure what count is for. This is the ship X high byte. The level flag, we use that for the end of the game, and the animation count, we use that for animating the sprites, so that's all zeroed out. Then we're going to show the sprites. We'll look at that routine later. Decompress the level data, and then we're going to draw the level, make level, and we'll look at those routines later. Got a long way to go before that. And then we're going to read DO1F is the sprite to background collision detect. Loading it clears it. So that's just to make sure that there's no erroneous hardware collisions between the sprites and the background. We're actually going to use that in this game. Many commercial C-64 games did not use the built-in collision detection because it has several flaws. But for this particular game, it's fine. I think I saved some space with it. Okay, our wait IRQ routine, we'll look at that in a bit, show the score, and do sounds. Okay, so we've now entered the main game loop. So we're talking about that nesting. Now we're all the way down to the most granular part, the game loop. And this is what runs 60 on an NTSC machine, 60 on PAL, 50 times a second. Most commercial action games have a one-to-one correspondence between their game loop, where the logic is done, and the display code, which is what allows it to smoothly animate. Now, if a game has to do too much, it can't run at a full 50 or 60 frames per second, but many do. And the idea is that you have a tight game loop which runs, and it is updating all the game state, and that displays it as well, or updates the VIC registers, so it's all displayed. Okay, so these are different subroutines that are called every frame, like waiting for the scan line. We'll look at those in more detail, and this do sounds updates the sound effects because they're kind of dynamic. And we'll look at those later. And now, collide. Check the collision register, and we have to store it in temp. That's because when you read the collision register, the VIC collision register, it automatically clears it. It resets any collisions that have happened. And if there's multiple collisions going on, then you're going to lose that data. So I'm saving it for later. Now we're checking the lowest bit. If it's 0, then we need to go check the building. But otherwise, we know that the ship hit a building. And that's kind of the convenient thing about, in this game, it's so simple, with just the one alien ship and the one bomb falling. We know that either the ship hit a building or the bomb hit a building. If the ship hit, then that's game over. So here's the game over text. It's just calling that same AB1E, that kernel routine that prints set to the game over text. And then we're going to wait for the joystick to be moved in a direction. I did that because if you're hammering the fire button and you get game over, then you might accidentally restart the game and not even get to see your score. So, kind of not a great way. You have to push the joystick any direction. That's not the best. I should have done a delay loop, but this, I think, saved me bytes. Okay, and once the joystick has been moved, that's just an endless loop. Then we're just going to jump back to the play initialization to start a new game. Jumping back to one of those outer loops. Okay, so that's the whole game over sequence right there. Very simple. It says explode ship. I don't even animate that. It just kind of freezes. Again, I was in a hurry. I was out of bytes. Okay, now we're going to check. We stored the collision register in temp, and now we check the second bit, and if it was not equal to 0, that means if it was a collision with a building, then we're going to deal with that. That means that the bomb hit a building. Otherwise, no build. That means that we go ahead. We're going to see that later on. So this just checks, did a bomb hit a building? Yes. Here, we're going to trigger a sound effect. We load the frequency counter. We'll look at that routine later. Basically, that starts a sound effect playing. We're going to look at the Y position of the bomb. That's stored here in the VIC register for the sprite 1 Y position. We're going to subtract 30. The first fully visible sprite position is actually 50, but I think because the bomb is about 20 pixels down, yeah, I'm sure that's what it is. Basically, this has a bit of math built into it. The Y position is the top of the sprite, but by the time you reach the bottom of the sprite, that's another 20 pixels, so 50 minus 20 is 30. Will this be a prob? And then we're going to take that Y value and divide by 8. We're shifting it to the right 3 times. If you shift a binary value to the right once, that's dividing by 2, then dividing by 4, then dividing by 8. And whenever you see dividing by 8 like this, you are probably converting from pixels to characters, because there are 8 pixels per character. And then now that we've shifted that, basically we've converted from pixels into character coordinates. And then we're going to keep that in the Y register for now. And then we set the sprite, the bomb sprite, back up at the top of the screen. So we reset its position off screen. Now we're going to set the 0 pointer to the top left of the screen. And then there's this kind of terrible loop here where for each Y, so say we calculated that the sprite position is 20 characters down the screen. The screen is 25 characters tall. So say the bomb's fallen all the way down to the 20th row and a collision is detected. We're going to just keep decrementing Y, and for each time we're going to add 40 to the screen position. And then this is carry. I could optimize this better. I don't know why I didn't. And then we jump back to loop. So this is a pretty terrible little routine that just adds 40 repeatedly. There's other ways I could have done this. A table lookup. I could generate a table. Even this code could be optimized. I don't know why I didn't. Anyway, that's, if I ever revisit this game, then obviously I'm going to clean that up better. Maybe I just wrote the most simple version I could, and then I ran out of time, or I didn't have the need to optimize further, so I didn't. Okay, so that calculates. Now we have a 0-page pointer to the correct row, but at the left edge. Now we have to figure out the X position. We're going to look at the bombs, the high bit right here, and shift that into temp. This is a bit ugly. But yeah, this is taking the high bit of the bomb X position, the 9th bit, and shifting it to the right one, so it becomes a proper 9th bit. Here it's actually like a 10th bit because of how all the bits are packed. Some of this is hard to explain. And then we're going to take the bomb's actual X position, the low 8 bits of it, and we're going to subtract 12. Well, I'm sorry that I can't fully explain that. I'm quite sure this has to do with the edge of the screen, but I'm not sure why we're not subtracting 24 here. Is it because of the shift already in here, or is my math bad? Oh no, this probably isn't. Well, it might be the border. Maybe that's just half the width of the sprite, because we're converting from sprite coordinates into the screen position. Okay, and then we're doing some math here. Sorry, this is going to take forever if I explain everything, but basically we are again converting the X position of the bomb into character coordinates and mixing in the high bit because it's some 9-bit math. I'm not sure I did this right, but it seems to work. Here's the divide by 8. What are we doing here? Throwing it away and then shifting it again? Wow. And then we're putting it into Y. Okay, and now we have an X and a Y position. Well, we have the correct row stored in 0 page 0. And the Y is the X position. Okay, and there just isn't a comma X variation of this. So we're going to use Y. This is knocking out part of the building. This is the top left corner of where the missile hit, and then we're incrementing Y, and this is the right part of the building. The buildings are 2 characters wide, so we're just zeroing them out. And then we're adding 39. We're taking that X position, putting it over in A so we can add 39, which makes it wrap around to the next column, not adding 40 because we're doing 2 characters at a time. So 39. And they're basically, it's all the same code 3 times in a row, and that knocks out a 2 wide by 3 tall section of the building for each successful bomb hit. Now here we are adding to the score 10 points for a successful hit. And again, I could optimize this by checking for a clear carry and branching ahead, and then incrementing the high byte of score. I don't know why I didn't do that again. Just premature optimization is the root of all evil, or whatever they say. Okay, so now no building, or of course we did process the building. Basically this is continuing on. We're done with collision. We're going to move the ship, and we're adding the speed of the ship to its X position, and the speed is currently 3, and then we're going to add the high byte again. This could be optimized with that same increment trick, branch and just increment. And now we're checking for the high byte if it's equal to 3. Now I mentioned before that rather than ship X representing the pixels, it represents the number of half pixels. And so if the high byte is 3, that means we've reached 300 hex, which is about 768 decimal, but then we divide that by 2 to get the actual number of pixels, so we're left with 384. So this is checking for the wraparound. If the sprite has traveled 384 pixels, 320 pixels is the visible area, but then there's room for the sprite to go smoothly off screen and then wrap around. So if we're hitting that distance, if not, just go ahead to done. But if it is, we wrap the ship X position back to 0, back to the left side, and then we load the ship Y position and add 12 to it. I talked about how the building, we knock out 3 rows of it, 3 characters worth. Well, that's 3 times 8 is 24 pixels. So each time the ship wraps around the screen, it also drops down 12 pixels. That is 1/2 how high the building, of how much of the building gets knocked out. And I selected that number just because it seemed balanced or challenging enough. Okay, so the ship sprite movement is done. The speed of 3 is actually 1.5 pixels per second. This is how we do fractional math in assembly. It's look up fixed point notation. You could have like 8 bits of sub-pixel precision. That's called for in some games. In this case, it's just when 1 pixel per frame is too slow and 2 pixels is too fast, 1.5. Okay, now the ship animation. So this is just a counter. Oh yeah, that's what count is. We're incrementing the count and we're ANDing it with 1. So this means it's only every second frame. Basically, when you're checking the low bit, every other frame, this is going to be true. So this is a way of slowing down the animation, so it only updates every second frame. That is 30 frames per second. So if it's equal to 0, we're just going to jump ahead to done. We're not going to update the sprite animation at all, the ship animation. That's just a simple way of doing that. Okay, and then we have an animation count. This is like the frames of the animation. We're going to increment it every other frame. If it reaches 6, then we set it back to 0 again. So there are frames 0 through 5, 6 different frames that ship is animating, that pattern on it that you saw earlier. And then we're going to use that into a table. We are simply loading some pixel data, or actually a byte. It's actually 8 pixels worth, or 4 multicolor double wide pixels, and then storing them directly into the sprite animation. So there's actually quite a bit of code here. Now the alternative to all this code is to just put those sprite definitions right into RAM. But each one of them takes 64 bytes, 6 frames of that. 6 times 64 is, what, 384 bytes. But I think this code to update it is probably about, I don't know. This is what, 5 bytes, 10, 15, 30, 40, 50. And then there's these bytes here, which are 636. So I don't know, we're somewhere around like 90 bytes to implement this animation, but it would be 384 to implement that animation otherwise. Okay, so that's why I implemented in code. We saved quite a few bytes that way. Moving on. Now we're checking for the fire button. So we're reading the joystick register and just looking for whether the fire button is pressed, and there's a flag. And the reason for the flag is we're also looking for the fire button to be released. So we're just keeping a flag, meaning just like a bit, on or off, 0 or 1, true or false. And that flag is helping us keep track of whether the button has been pressed, or here released. Then we check for a press. And if it's not pressed, then we are done. And if it is, then we set that flag again. So basically this prevents the fire button from being mashed and also requires us to release the fire button for each bomb drop. This bit of code here is checking for the current bomb position. If it's up at 0, up off the screen, that's where we keep it until it gets dropped. So we're also checking, is it currently falling? And we also don't drop a new bomb if one is already flying down the screen. And now we're going to take the position of the UFO and copy that into the bomb. So the bomb will drop from the bottom of the ship. And we're also going to set the bomb's X position to the same as the ship right there. Okay, so when a bomb is dropped successfully, we're copying the position of it based on the ship. And then we're also going to trigger some sound effects. Okay, that's done. And this is moving the bomb sprite. We're just going to take the current Y position of the sprite. And if it's up at 0, we're not going to move it. That's because that's its waiting spot up off screen. Otherwise, we're going to move it down 4 pixels per frame. And we're checking for it to hit the bottom of the screen. That's if it falls right off screen. And if it does, we're resetting it to the top. So we're just using a Y position of 0 as the holding spot for the bomb. Okay, and then we're going to call this show sprites, which actually doesn't show the sprites, it more correctly positions the sprites. We'll get to that soon. Okay, now we're going to check, this is clear level, but really this is checking if the level is clear. And we're just going to scan the very bottom line of the screen. That's screen plus 960 is the bottom row. And we're quickly just doing a scan through that whole bottom line, looking for it to be all blank. And this is a much more efficient way. Rather than scanning the whole screen, which would be very CPU intensive, we can just check the bottom row. And because of the way the bombs fall down, if the bottom row is clear, we know all the ones above it are also clear. And so if we find something that isn't 32 blank, then we know we can jump ahead to done. That's way down here. But if it is done, the level is complete. And we set this level flag. We put the speed in level flag. This is a bit weird, but this is, we want to set the horizontal, the speed, that's the horizontal speed of the UFO, to 0, so it will stop moving. And you saw before how the ship lands at the end of a level. This is code to control that. So we're zeroing out the speed to prevent it from moving to the right. And we're kind of doing we're setting a level flag to a non-zero value. Rather than keeping the speed elsewhere, we're temporarily putting a level flag, which tells us that the level is over. That's what it's using right here. And we award the player a bonus 3 points for each pixel that the UFO is above the bottom of the level. And then we just keep adding it to the score. Oh, here, I finally do that little trick of taking care of the low byte and then branching ahead and only incrementing the high byte when necessary. So there, I finally do that. Okay, and we increment the sprite Y position and we check, did it hit 229? That's the bottom of the screen. If not, then we're branching ahead to done. This might be a bit confusing, but we're allowing the whole game loop to keep playing, but we've taken control away from the player, and now the ship is going to descend, but we're still going to be updating the score and so on. So this is what makes it smoothly animate. We're only moving 1 pixel per frame until the ship lands at Y position of 229. It's an important thing in game design. You can't just make a tight loop without allowing the whole game to keep updating with the vertical blank and waiting. You're splitting a task across many frames. If you just did a tight loop, it would just snap the ship right down to the bottom. And this is a nice little, I think it's kind of a nice little touch to see the ship land. Okay, and then once it has reached the bottom, then we're going to take that level flag and put back in the speed, update the score, wait for the joystick to be pushed, and then go to level initialization, which starts a new level again. It increases, updates the screen and all that. We looked at that before. Okay, and if it's not the end of the level, we're just going to go, well actually whether it is or not, we're going to go back to game loop and run the game loop. Oh, so that is done. Now we have to look at a few specialized routines here. This has taken forever. We're going to build a level by going to the bottom row of the screen, and we're going to do 40 positions across the screen and 20 rows up. The maximum height of the building is 20. And we're just going to keep decrementing X. If we've done all 20 rows, then the level is built. If not, we're working from our right, 1 row at a time, and we're going to load the level data. We're going to look at where that comes from soon. But basically, we are just grabbing the level data and repeating this loop. So this is a loop that's going to scan from the bottom right corner all the way to the bottom left, and then go up a row, and so on. And for each row, we've got a bunch of counters that show how high the building should be in that level. And here we draw the right hand side. That's just the character. That's the right edge of a building. And we're storing it on the screen. And then we're drawing the left side of the building, each of those columns, and continuing on. This is, if we wanted better graphics, this is where we would improve it. If we had some custom character set and some more variety in the buildings, this is where it would have to be done. So this is all the code that draws that level on screen. There's just a bunch of counters for the height of each building, and they get decremented until all the buildings have been drawn and we reach the top of the screen. And this is where we move up to the next row. We're subtracting 40 each time instead of adding 40. And here we're checking that we've reached the top of the screen. This is the high byte of the screen -1. And now that actual level data, we still have to figure that out. This is called decompress. And there are potential, because each building is 2 characters wide, there are 20 positions. There are 20 different potential columns, building columns. And we take that level pointer data that I talked about quite a while ago. I talked about how each level is defined by 10 bytes. And now we load the level data. Let's go look at that. It's just down a little ways here. So this defines each level. And each nibble is the height of that building. So there's no buildings on the extreme left or right of the screen. There could be, but I found that was too tricky to hit. So there's always 2 buildings on the left and 2 buildings on the right that are just not there. Their height is 0. And then the buildings are 2 and 1, 2 and 1. So each nibble defines the height of the building at that position. So these are all quite low buildings, a maximum of height of 3. Then the next level, there's some buildings that have a height of 4, 5, And on that last level, there's even some buildings that have a height of 6, which is the maximum. So that's all it is. There are 10 bytes which encode 20 buildings in each level, and a total of 50 bytes. And I kind of hand designed each of those levels to be kind of, at least to me, interesting or fun. Okay, gotta go way back up here still, and this is the decompress. So this is where we take those nibbles, we grab some level data, and we take the high nibble, shift it down to the low, and then store it in the temp, and basically put it in the level, and then we get the low nibble, and then also store that in the level. So basically we're decompressing those 10 bytes, turning them into 20, which are counters for each height of the building, and then the routine above is what draws those out. Okay. I know I'm kind of skimming over that, but that's the general idea. It's just decompressing each nibble. And this is a wait IRQ. That's actually totally the wrong name for it. I don't know why I was still calling it that. There's no IRQ here, but this is waiting, more like wait VBL, waiting for vertical blank. You're waiting for the raster line DO12, holds the current raster line as it's drawn. So we're waiting for raster line 224, which is right down near the bottom of the screen. So that IRQ, that was an old habit of mine. Really, it should say something like wait for VBL or whatever. Here's one for a wait for joystick. So this is while we're waiting for the joystick to be pressed. Well, wait for the joystick to be moved. Notice that I'm calling do sounds, otherwise sound effects won't continue to update because this has taken control away from the main loop. So I had to keep calling the do sounds within here. And here is the do sounds. And I don't think I 100% remember how this works, but I got a bunch of frequency counters, which I'm decrementing, and you hear those sound effects, everything drops in pitch. So that's what we're doing here. We're just, as the frequency counters drop down, we're waiting for them to hit 0. And then once they've reached, we're storing them in the voice 1 and voice 2, the high frequency. The low frequencies for them, I believe, are just fixed. So we're just going, yep, just like that. Basically, it's just decrementing the SID registers for those sound effects. And that's what, again, just like the sprite movement, we need to spread the change over many frames. So that's what these various counters do. You're just doing small changes that add up into a big change over a second or two. If you just did it all in one tight loop, it would be probably inaudible. Here's that show sprite routine. This is where we're taking the ship X position and we're dividing it. The high byte, we divide by 2 and we store it into the sprite X position. That's kind of convenient that it's there. This is a bit ugly. We're going to load in the ship X. Again, we're going to rotate it and we're going to store it in the X. So this is just dividing that ship register or that ship position by 2. So I was talking about earlier to map it from my double, twice as precise pixels into actual pixels. And we're just doing the same with the bomb X position as well, with a bit of extra funny business to map that high bit into its correct position because these registers are shared. Okay, so that's that routine. Show score, we're just going to display the score. Again, this is just the same as we saw earlier. We're printing the word score here, AB1E, and then we're actually printing the score again using that routine. This time we're using a 16-bit value. That prints it. Trigger voice, this is how we initialize a new sound effect. Well, and there's the level data, and we already looked at all that. That's the animation table. Okay, that was epic. I've been recording for 75 minutes, I'm sorry I skimmed over some of that. Like I had said at the beginning, this might be a bit of a lesson in how am I going to approach this for my even more complicated, bigger games like Splatform, Minima, Frogs and Flies. Those games are even bigger. And I welcome your feedback. I hope this was still a useful insight and into C-64 game development. Is it too much? Do I need more detail? I welcome your feedback. Like I said, I want to make videos about some of my other games, but if it's just a jumbled mess or there's just too much information, maybe I need to narrow it down and just look at a certain part of it. And like I said, you can download some files. There'll be a link in the description so you can look at this code yourself and try building it, play around with it, and we'll talk to you next time.